We're moving on to our last speaker for today. We have Susanne Glaser from GFZ. The title of her presentation is Rigorous Propagation of the Galileo-based Terrestrial Scale. And
yeah,
I am one question. All right.
yeah,
Susanne,
I cannot. Yeah, thank you.
Yeah, you have the floor.
Okay, thank you very much, Myra. I will share my screen. So do you see it in full screen?
Yes, perfect.
Okay, so thank you again, and hello everybody, and also welcome from my side. It's my pleasure to present the study Rigorous Propagation of a Galileo-based Terrestrial Scale on behalf of my co-authors. This work started during my research stay in Paris, and I'm very glad to be part of it. So the presentation is divided into 4 main parts. After some background information and motivation, I will give you a few details about the applied method, then the resulting scale factors with respect to IGS R3 and ITRF 2014, and the presentation will be concluded by a short summary. So let's start with the introduction. So far available GNSS satellite phase center offsets, these PCOs, were estimated with fixed ITRF scale. And therefore, by convention, they depend on the underlying reference frame, so on the SLR and VLBI scale. So for previous ITRF solutions, as you have already heard, no independent scale realization was possible by GNSS. However, as Zuheir already mentioned, due to the disclosure by the European GNSS agency of the metadata, including the PCOs in radial direction for the satellites for Galileo, this opens a unique opportunity to realize an independent scale in multi-GNSS solutions and possibly contribute to the next ITRF scale, the ITRF 2020. Some words about preliminary work. So for the IGS R3 UNTEX file, one single correction common to all IGS 14 UNTEX GPS z-PCOs was estimated based on a preliminary solution. Like in all other UNTEX files, the satellite z-PCOs are constant, so except for 2 satellites, and also important, no uncertainties were available. So it was not possible to constrain these PCOs with appropriate weighting. They needed to be fixed in the repro-free solutions. So to overcome these shortcomings, we defined a new approach in this study. So we would like to fit deterministic and stochastic models to the time series of the GPS and GLONASS z-PCO estimates, derive piecewise linear models of them instead of just being a constant, and then introduce these time variable z-PCOs with realistic uncertainties, and then have hopefully a better scale. Then let's move on to the method. So the data used in this study is based on the IGS repo-free SINEX solutions of 4 different analysis centers, namely CODE, ESA, GFZ, and GRGS. If you look to the time span, especially covering of the Galileo time span, and having in mind that the constellation continuously evolved, one might wonder when actually can we assume a Galileo-based scale to be precise and stable enough. To answer this question, a preliminary step was done. So 2 cases were considered. Here you see this for all 4 ACs, and let's concentrate on one plot here, for instance, code. The black dots show the GPS and GLONASS z-PCOs fixed to IGS or free Antex file as a first case, and the second case in red, the Galileo z-PCOs were fixed. And you can see that after May 2017, a steady level can be achieved when at least 17 Galileo satellites are included. Okay, then with this information, we would like to get z-PCO time series. So we distinguish here before and after May 2017. After May 2017, the Galileo satellite z-PCOs were fixed, with one exception, to the values provided by the GSA, and the GPS and GLONASS z-PCOs were freely estimated. Before May 2017, an additional constraint was applied, and you can think of this constraint like a no net translation condition, which was applied to a selected set of GPS and GLONASS satellite z-PCOs. Then we have time series of GPS and GLONASS satellite z-PCOs. And before next steps, an initial screening procedure was done. So data before 1997 was eliminated, and also other data. And as a first result, here you can see time series plots of individual satellites, for 2 here in this case, for ESA AC. On the left for the GPS satellite G33 as a rather good example, and to the right of the GLONASS satellite R730 as a rather challenging example. What we do see is that there are diverse features. We have periodic terms, we have offsets, outliers, slow linear variations. And as these features are superimposed, it might be challenging to fit models to these time series. However, we did that. And we fit deterministic and stochastic models to these time series. And we started with an initial model consisting of a single linear trend and variable white noise. Then, step by step, iteratively, this model got refined and augmented by adding more deterministic and noise components. And as an example, you see here z-PCO time series for the satellite R730 for ESA AC. So we took into account these offsets. So for every segment individually, the model was fitted. And here, the last row, you see the residuals. Another thing what I would like to show you here are periodograms. So we calculated average periodograms per constellation for GPS and GLONASS per AC. You see it here for GFZ. And let's focus here on the black curve. These are the average periodograms of the residuals from the piecewise linear models. So this means the periodic terms are not included in this model, so they're included in the time series. And what we see is draconetics. For GFZ here, for GPS and GLONASS up to the 12 harmonics. We also see signal here, probably due to artifacts in the M2 ocean tidal loading. We also see here for GLONASS spectral comps on 8 days, 4 days, 2.6 days. For all these signals, we try to give explanations. I will not go into detail here. Just these average periodograms helped us to fit the deterministic models. And with all that information, we have deterministic and stochastic models. And in the end, we want to have a scale. So all this information somehow needs to get back substituted. So how was this done? I call this long-term stacking of GPS and GLONASS z-PCO time series. So maybe you remember in the beginning, I said before May 2017, an initial constraint was applied. So this no net translation constraint. However, we would like to have our piecewise linear Z models to be independent from IGS or free untext file. So therefore, on a daily basis, transformation parameters were estimated to remove this initial constraint. So then these new piecewise linear z-PCO models get back substituted in the daily AC SINEX solutions, and the resulting scale is compared to that of the IGS or free reference frame. So as a result of all that, we have a Galileo-based scale, which is independent of IGS or free untext file, and also of the SLR and VLBI scale, so our initial goal. Now let's move on to the results. Here you see in black the scale factors with respect to IGS or free in millimeter. So the full time series. To this full time series, a model got fit. So in red, a deterministic model consisting of an annual and semi-annual sine wave, linear trend, of course. Then in green, also a stochastic annual component, pink power law noise, and in cyan, variable white noise. So in this model fit, also a linear trend was estimated, and this I will show you here on this slide. So for the 4 different ACs considered in this study, a mean scale offset at epoch 2010 and scale rates with respect to IGS of free. What we do see is that there are differences among the ACs. However, they are quite small. What I also would like to point out is that the uncertainties reported here do not only contain the noise based on the time series I showed you in the previous slide, they also contain information from the piecewise linear models. Yeah. So this is with respect to IGS or free. Let's have a look to these results with respect to ITF 2014 for our 4 different ACs and also for the IGS repro free solution with constant z-PCOs. So we see that with respect to IGS repro free, these scale offsets are about in the same range. We also see that all 4 ACs agree within 1 millimeter for the scale offset and 0.1 millimeter per year for the scale rate. Then another comparison with respect to the other space geodetic techniques. So in red, VLBI, in blue, SLR, Doris and Susanne, pink, the constant z-PCO GNSS scale, and in green with piecewise linear z-PCOs for GFZ as example here. Okay. Then I would like to come to the conclusion. So in this study, we rigorously evaluated all GPS and GLONASS satellites at PCOs. We derived piecewise linear models of GPS and GLONASS at PCOs. They get back substituted to the repro-free solutions, and we got a refined Galileo-based scale, which is characterized by these 3 points. So the differences to IGS of free Antex-based scale are essentially linear. The 4 ACs agree within 1 millimeter for scale offset and 0.1 millimeter per year for the scale rate with respect to ITF 2014. And the refined AC specific estimates agree with the scale of IGS repro-free solution within the same level. And one remaining question is if and how this will contribute to ITF 2020 scale. And with this slide, I would like to thank you very much for your attention.
Thank you very much, Susanne. We do have a couple of questions for you. So one comes from Tom Herring. Did you have numerical trouble removing PCO constraints from the GFZ SINEX 1 to the minus E7 meter?
I'm not sure about that. Sorry, maybe we can discuss this offline.
Can I answer?
Or Paul, please, yeah.
Yes,
yeah, the
absolutely.
answer is no, not particularly. We didn't have trouble.
All right, so the next question, it actually comes from 2 different participants. So Octavian Andre and Wen Huang asked a similar question. Thanks for the nice presentation. What's the reason for excluding E102? And a second question from Wen Huang, besides the possibilities mentioned in Paul's answers, it's like example, aging of the antennas, did you have any other assumptions for the reasons of unconstant z-PCOs?
Okay, so first question, I think this was not stable enough, this satellite. Paul, you can maybe correct me.
Yeah, and, from the preliminary solutions that were used to before repro-3, it appeared that the PCO of that Galileo satellite estimated in space disagrees with the published value by GSA by, I don't remember the exact amount, several centimeters, maybe 10. So while for the other Galileo satellites, the in-space estimates of their z-PCOs were in much better agreement with the values published by GSA.
Okay, and then the other question for this aging of the antennas. Yeah, so this might be a problem as far as I understand when all satellites have a common feature, and then we would see this trend also in the scale. But if it is just a problem per satellite, then this is maybe not so problematic. So maybe maneuvers or mass loss of the satellites, I don't know. This is, if it is just a single satellite, might be not such a big problem as far as I understand.
Okay.
And we have the trend under control with our assumptions.
So we have some more questions. So next, has there been any discussion on how to validate that the chamber Galileo corrections are the same on orbit? For example, are they absolutely correct? And the question comes from Anthony Siport.
Yeah, so this is a basic question. So I know what you mean with that, because we completely rely then on these values. I'm not an expert in telling if it is really the case, but yes, this is an assumption we make.
Can I add something to your answer to that?
Yeah,
we could not verify that the published values are in agreement with PCOs in space in an absolute sense. We don't have a way to do that, except by comparing with SNR or VLBI. But what we could verify is that relatively to each other, the the z-PCOs published by GSA are consistent with those in space, except for that particular satellite E102. And yeah, the dispersion of this agreement is around 3 centimeters.
So next question, it's from Jim Ray. Susanne, why did you associate the 13.62D line in your GPS spectrum to the M2 tide? For daily samples, the M2 period aliases to 14XD.
Yeah, so this we discussed with Paul, and he did some, let's say, simulations how this period of the M2 ocean loading propagates to orbital errors. And Paul?
Yeah, 13.62 days, that's basically the aliasing period of M2 through the ground repeat period of the GPS satellites.
Okay. Another question for both Susanne and Paul from Alvaro Santamaria. How did you separate the actual variable white noise series and the power law noise series contributions to the observations? That seems like a very cool thing to do, but I do not understand how is it possible. Thank you.
Okay, so maybe I first, then Paul. So as far as I understand, this was iteratively done. So first we started white noise and then white plus flicker noise, and in the last step, so in this model fit, is in principle 3 steps, and in the last step then this was to focus the noise, and in this last step also the power law noise, so this kappa index was estimated. And I don't know if Paul wants to add.
Yes, I think Alvaro's question was once the noise model is estimated, how can we separate, how can we estimate the white noise in the series, the flicker noise in the series? And that's done by Wiener filtering, or generalized Wiener filtering. I can send you the equation, Alvaro, if you wish.
All right,
Okay,
thank you.
I will.
Yes, please. So we do have a couple of questions that are still related to Susanne's presentation. So I am going to go to handling column and then go back to the other questions that are more general for the panelists. So as preliminary results show some scale discrepancy based on Galileo and Beidou metadata, how would possibly inconsistence of PCO metadata released by different GNSS cope with in the future? So basically, how can you cope with differences in metadata between different GNSS service providers?
I'm not sure about that. Maybe someone else has an idea.
Any of the other panelists?
Can I have something to say on this?
Yes, absolutely.
I am not expert at all. When you have different approaches, different techniques that start to have answers to some scientific question, you need time. You need more data. You need to wait until we see more data from the satellite providers in order to answer such a question. That is my general opinion without being an expert on that.
Any other panelists? Okay, so moving on, we have a question from Urs Hogenthaler. It seems that the time dependency of PCOs capture time-dependent orbit modeling errors. If this is the case, should one then also try to estimate time-dependent PCO for Galileo with zero mean condition?
Might be an idea, I guess, but I'm not really sure, because I thought we rely on Galileo PCOs as they are. Someone else?
Yeah, I think it would be a good idea, Urs. And maybe one of our next steps.
Okay, thank you so much, Susanne, Paul.